Section 5.3, Normal Distributions, Finding Values. In Section 5.2, we found a specific z-score, which is really a specific deviation from the mean. And if we knew a specific z-score, we could determine the space under the curve for that. For example, if I was looking at a deviation of negative 8.3, we use this table right here. Here's negative 8, and I can go across to where 0.3 is up here. And negative 8.3 would simply be 0.2033 or 20.33%. However, we can also do this in reverse. We can find the z-score if we're given the percentage under the curve. Now, first, I want to remind you, the space under the curve on the table always goes from the very beginning on the left side all the way to that point we're measuring, which is right here. So when we do this, we want to find out how much space is under the curve. That's from the very left to that point. Now, I want to find the z-score for an area that corresponds to 0.3632 or 36.32%. And if I look across the slide here, what I got is, let's see, 0.3632 is right here. And if I look what that corresponds to, that is negative. I'm circling it also. Negative 0.35. So negative 0.35 deviations is equivalent to 36.32% under the curve. Now this next one here is a little interesting because it's asking for the measurement, of course, of the z-score, where it would be, but it's giving us information of where the amount of space is from the right. And we don't measure from the right, we only measure from the left. So we have to use some intuition to figure out exactly what's going on here. Because again, the space from here to here is what they're giving us, which is 10.75%. But we can only measure from the very beginning on this side, from here to there. But remember, the total space under there is always 100%. So what I can do is I know the total amount is 100%. And I know it's 10.75% from the right to that point. So I'm going to subtract 100% or 1 minus 10.75%, which is 89.25%. Or 8925. So I'm going to look up 0.8925 on my table. And basically, I can figure out if I look up at 0.8925, I can determine the z-score. 0.8925 happens to be where my arrow is pointing, which is right there. And that is a z-score of 1.24. There's my 1.2, and there's my 0.04. 1.24 is my z-score. And again, I looked at it's a positive z-score. It's a greater than 0.5000. So I know it's on the positive table from 0 to 3.4 standard deviations. 0.8925 is that area under the curve that's not shaded here. This one is also very interesting because it's giving us a z-score. What they want to know is the z-score where 95% of the distribution is between minus z and z. And what does that mean? Well, if I draw a little bell curve here, like this, on top, And here's my mean. It's not the best curve. But if I know I got -1 deviation here, and I got 1 deviation here, plus 1 deviation here, the thing I remember, it's symmetrical. So if my z is 1, then my negative z is simply -1. My z is -1 if my negative z is -1.8, then my positive z would be 1.8. And really what we're doing here is we're trying to find the space and wants to know the z-score of 95% in the middle. So in other words, the 95% permeates halfway going to one side from the middle, halfway going to the other side. So really what we got to find here is what the z-score is for 95% in the middle. Now, 95% in the middle, I don't know what the z-scores are, but I know, as I'm showing right here, from the mean or the middle, it's 0.9500. They tell us this. If I divide that in half, because this is symmetrical, I know 0.4750 is from the mean to the lower end, and then 0.4750 from the mean to the upper end. 0.4750 plus 0.4750 is 0.950. And then we know another thing here, and this is where some people get a little confused. I don't mean just students, I mean everybody. From the very beginning here to the halfway mark, my mean is 0.5. 0.5000. That's 50%. And I now know from the mean to this upper point is 0.4750. Well, 0.5, see if I can write this real well, 0, 0, 0, and 0.475, terrible 5, I apologize for that, 0 equals 0.9750, 0.9750 or 97.5% under the curve. And if I look up where 0.9750 is, it's right here. And that is 1.96. So my z, let me erase this right here. Done a lot of scribbling here. My z is 1.96 deviations. And if my z equals 1.96, z equals 1.96, then my negative z equals negative 1.96. There we go. So from negative 1.96 to 1.96 is 95%, which means the other 5%, because it only holds 100%, has got to be split up evenly, because this is split up evenly, between 0.0250 at the lower end and then 0.0250 at the other end, upper end. So 0.0250 plus 0.9750 plus 0.0250 is 1 or 100%. Now, often you'll see a letter P with a subscript of a number, and that you got here P subscript 90 or P90 refers to the probability of a normal distribution with 90% of the area under the curve. Well, 90% equals 0.9000. And again, like we just did in the previous sheets, it's greater than 0.5000. So I know it's on the positive z-score sheet. And I'm going to find 90. Now, here's where you got to be careful. There is no exactly 0.90. There's a 0.8997 and a 0.9015. Well, 0.8997 is 1.28 deviations, and then 0.9015 is 1.29 deviations. Which one do we pick? Again, I apologize for my writing. Very difficult in this mouse. Well, this, because the score I'm looking for is 0.9000. 0, 0. See if I can close that 9 up a little bit. That looks like a lollipop, but you get the idea. All right. This 0.8997 to 0.900 is only 0.0003 ten-thousandths away. This is from 0.9015 to 0.9000 is 0.0015. We always go, it doesn't matter if it's above or below, whatever is closest. And 0.8997 is closer than 0.9015. So we would select the 0.8997, and that is going to be 1.28 standard deviations. Here's a P at 20%. P at 20%, this is less than 50%, less than 0.5000. So again, I got my negative P sheet here, and I'm going to look at where the closest is to 0.2000. And when I look at this, the closest is 0.2005 by far. Lower end 0.2033, and then the upper end 0.1977. So that translates to negative 0.84 standard deviations, which is close to negative one deviation, but not quite. Now, what I've done here is we can rearrange to find the exact value of what a number is if we know the mean, the z-score, and the standard deviation. We were using this formula z equals x minus u all over sigma, or which is the individual amount minus the mean all over the standard deviation. All I've done is I've just multiplied out the sigma times z, rearranged this equation, and then added u. So if I want to know a specific amount where it would be, I use this formula, x equals mu plus z times sigma. So let's suppose we have a vet who's got thousands of cats coming in, and he's weighing them all over the years, and he finds out the mean is 9 pounds and the standard deviation is 2 pounds. Well, this is simply, used for, he can chart what kind of medicines he needs for the order, because animals of different size are usually given their vaccines, their shots, their medicine based on their weight. So you actually chart this to know how much he should get for each area. Now, he wants to know if a cat falls within 1.96 deviations, what's the corresponding weight? Let's take the formula. X equals my mu plus my z-score times my standard deviation. So the mu is 9 plus 2 times 1.96, which is 9 plus 3.92 or 12.92 pounds. So 1.96 deviations is 12.92 pounds. What if a cat falls in minus 0.44 deviations? Will be 9 plus 2 times negative 0.44, which is 0.88. 9 minus 0.88 equals 8.12 pounds. If a cat falls at 0 deviations, what's the corresponding weight? Well, 0, as I've said before, is the mean. You have minus 1 deviation on one side, plus 1 on the other. If it's 0, that is the mean. So the mean is 9 pounds. And we can prove this also. 9 pounds plus 2 times 0 deviations is 9 pounds. Now, training guide here. Let's suppose they have, and this goes true for every state. Policemen often have to take a test before they even go to a police academy. And what's interesting here is we read this. California police officer standard training normally have an average of 50 with a standard deviation of 10 on their test. Agency will only hire those in the top 10% of scores. What's the minimum test score in order to finish top 10%? Now, you got to keep in mind here, a lot of people make this mistake in general that, it's top 10%, that means 45 out of 54 score. No. What we're actually looking for is if we have an average of 50 and a deviation of 10, what is the score of the top 10%? They could score from 45 to 55, but they're only going to take the top 10% of the score. They could score from 20 to 30. Again, they're only going to take the top 10% of those people. So we need to figure out, based on the average of 50 and a deviation of 10, what is the minimum score they'll take if they're only taking the top 10%. We did this before. A z of 0.9000 is 1.28 deviations. And as I did before, it is right here. It's not exactly 0.9, but it's the closest, 0.8997. So 0.8997 is going to be my z-score. 50 is my mean. So 50 plus 1.28, which is that z-score, times 10, which is deviation, which is 50 plus 12.8, equals 62, about 63. The lowest score in the top 10% of the scores accepted would be a 63. So we may have thousands of officers taking this test with various scores, but if it's 1,000 of them, only 100 will get a score of 63 or higher. So this has nothing to do with what the result is in the test per se. It's actually what is the score of the top 10%. Finally, here's another similar example. A randomly group of females aged 20 to 34 with the mean total cholesterol of 179 milligrams per deciliter with a standard deviation of 38.9 milligrams per deciliter. We assume the cholesterol levels are distributed normally between the females aged 20 to 34. Then, what's the highest level of cholesterol a female can have and be at the bottom 1%? We've got an average here, a mean of 179. Our deviation is 38.3. And 1% is less than 50%. So I'm going to look for 0.0100. Whatever is closest to it. And the closest number here is 0.0099. That's only one off, one 10,000 off of 1%. This is 2 1,000s off. So we're going to choose this one, 0.0099, which is a negative 2.33 standard deviations, which is what I got here, 1%. I got my mean of 179 plus negative 2.33 times my deviation of 38.9. 179 minus negative 2.33 times 38.9 is 90.637. 179 minus 90.637 is 88.363. So a person in the bottom 10%, bottom 1%, if the cholesterol level is 88.363.